You have fallen into Event Horizon with John Michael Godier. Joining John today is Dr. Brian Keating. Dr. Keating is a physics professor at the University of California, San Diego, and the director of the Simmons Observatory, specializing in the study of gravitational waves created during the early stages of the Big Bang. Dr. Keating is also a pilot and is the recipient of the 2007 Early Career Award for scientists and engineers for his work with BICEP.
My question for you to start off this beautiful part two, my question for you is, given our previous conversation, do you think it's possible that we live in a universe where we're the best it gets and that aliens, if should we ever come across them, are much worse than we are?
Well, that is actually, I always have this kind of a subroutine running in my mind when I'm doing an interview. And I want to know in real time, does the person I'm talking to, do they think I'm an idiot? Do they think I'm really smart? Are they enjoying it? How do I know I'm doing a good job as a podcaster? And one of the ways I know I'm doing a good job is they say, I never thought about that. And so I'm going to give you the highest accolade that a Keating can give to a fellow podcaster. And that was a question I've never really thought about. Are we the best it gets? I think the fundamental question we have to really grapple with is, are we the only thing that the universe gets? Are we the only form of life? Are we the only form of conscious life? Are we the only form of technological life? Are we the only type or form of moral life? In other words, life that can make decisions and act in a way that is furthering some metric of flourishing. And I think that the most honest answer to give to all those is that, yes, we are the only the only form of life that exists in the conscious, moral, ethical, technological realm. We're certainly not the only life that exists in the universe as human beings, because we know of billions or millions of other species. So, but the point being, I think that scientifically, this notion that there's somehow teeming evidence that the universe is teeming with not only life, but when we think about a technological or some sort of advanced civilization, many millions of years perhaps beyond ours, I think, well, the fact that any good scientist should admit is that there's zero evidence for that. And what you normally get is, well, but the universe is so big, and even as Carl Sagan and my past guest Ann Druyan said in their wonderful book, Contact, if there is no life, it's an awful waste of space. But the universe is under no obligation to obey your metrics and your judgment of how it should utilize its space. So I think it's really kind of anthropocentric, which we should have gotten past many centuries ago with the likes of Copernicus and Galileo, moving us from the centrality of the position that we had enjoyed for millennia. So I think that until we have evidence that life exists, and then we have evidence that life is somehow technological or advanced, we're in a very primitive state. Now, that is not to say by any means we should not, A, be looking. We should not be trying to simulate conditions. We should not speculate on what those civilizations might be like in terms of their culture, their civilization. I interviewed Art Kirschenbaum 6 months ago or so, and he has a wonderful book called A Zoologist's Guide to the Galaxy, which he speculates on all the different cultural, societal, physiological elements and attributes that you would expect an alien civilization to have. And in that, there, I would say, would be kind of equal likelihoods or probabilities for them to be better than us or worse than us in terms of the metric that you initially asked the question with. But I think the ultimate thing is that we have to get over this naive supposition that just because the universe is big, it's teeming with life. And just because you multiply an enormous number, the number of planets in habitable zones, the number of square kilometers of surface area there's so many more variables that go into conspire against such a civilization that it really is multiplying an infinitesimal by a large infinite number, perhaps. And that, as you know, for mathematics is basically undefined. And to further that, if you want to include this, I always say, if you just look at the Earth and say, instead of considering the whole universe or even the whole galaxy and saying it's so big, there's got to be life, look at the Earth. There's 7 continents. I've been to 6 of them. And the last one to ever be reached and discovered was Antarctica. And I spent 2 months of my life there probably. It is a big, dead, flat, white, inhospitable place with extremely low amounts of life on it compared to its surface area. Its surface area is about the size of, say, 2/3 of North America, a couple times the size of Texas or Alaska. It's quite large in terms of the land area of the Earth. Don't forget, 70% of the Earth is covered by ocean and completely uninhabitable by technological life forms that can make semiconductors and do kind of plasma welding and do metallurgy. I mean, you can't do that in the ocean. At least you wouldn't start ab initio from the ocean. We may go there in a Kevin Costner like Waterworld, but let's not get into that. So you asked the question, well, Earth is really big, and let's take the landmass on Earth and let's take 1/7 of it, and let's just approximate that. You'd expect 1/7 of the life to be there if these arguments actually held water, but they don't, no pun intended, or hold ice. So just the mere capacity for life is by no means indicator of the probability of life. So to answer your question, if there is life, which is the biggest if imaginable, and an if that should be pursued with great gusto, as many of my colleagues and guests are, if there is life, there probably is an equal chance as any that they'd be better than us than worse than us.
Setting foot in Antarctica as a scientist, did you look around and say, this is as close as I'm ever going to get to standing on an alien world?
It certainly what felt like that. When you're at the South Pole Station, built by your listeners' generosity and largesse through their tax payments to the federal government, the Amundsen Scott South Pole Station is built up on stilts. It's kind of mirrored reflective to keep away some of the sunlight, make it more visible from great distances by approaching potential rescue crews. And there are essentially no life forms other than red-jacketed Canada Goose wearing individuals traipsing about, and an occasional metallic albatross called a C-130 Hercules that lands on skis, the only place on Earth that they operate such planes to good approximation. And the people that are there are trapped like astronauts on a space station by their own desire and volition. They want to be there. There's a fierce competition to spend 11 months or more of your life locked away from society, immunized and isolated at the bottom of the world with only 49 other people, perhaps. And this attracts a very special type of person, both in terms of their physiology and their psychology. And to be there with those types of people, the highest performers, these are people that come in third in the Boston Marathon. The one year I was there was a guy who had come in third, who's like a plumber or carpenter or something like that. And then all these buff and nerdy scientists that, there's the reason that the station exists in the first place. And then you could realize that you're on a continent, John, and there's only 200 other people on the whole continent in the wintertime. It's insane. And the continent is so vast, so flat, so white, so forbidding, and all the extremes, including the high altitude of the South Pole, that yes, it's very much as close as I'll ever get to being on another planet's surface, if that planet were like Hoth, this icy planet.
Now, do you think that this has a significance, especially in the modern age, of there are people willing to go to Antarctica and live there and even weather the long Antarctic night? Do you think this tells us that, yes, in fact, there will be people completely willing to go to the moon and Mars on these fancy new rockets we're building?
Oh, there's no doubt. In fact, I know one of the people that Vegas and maybe even my own kind of heart is handicapping to be the first woman to be on the moon, and that's Dr. Jessica Meir, who, kind of the inverse of me, she went to Brown as an undergraduate. I was there as a graduate student. And then she went to UCSD as a graduate student. I'm here as a professor. And she's an amazing individual. I talked to her live when she was on the space station for almost a year, flying over San Diego about 2 years ago. And she's just an incredible individual, an athlete, a pilot, PhD oceanographer, scientist, ambassador. But she also, to my mind, I don't believe she's married. I don't believe she has children. She's in her early 40s, and she's dedicated her life to this mission of serving and exploring the universe. And she's not alone. There could be part of the mission of the Artemis project is to land a woman and a person of color. The competition is so fierce. I mean, as Elon Musk has said, he hopes to die on Mars. And as one of my guests, Martin Rees, the Astronomer Royal of the United Kingdom, said, I just hope he gets his wish, but I hope it's not on impact. So yes, there's many people. The world's richest man, the richest person in human history, is willing to give up all the comforts that munificence could buy in order to spend a year perhaps in a can going to Mars and not ever coming back. And this is an individual who we now know has somewhere between 9 and 10 kids, somewhere as many wives or jilted lovers, and has no shortage of ambition to give it all up to go to another world.
Yeah, not me.
Me neither. Although when the kids are acting up, John, I sometimes consider it. If I could bring the wife and the kids, get away from it all, maybe. No, I'm not going to do it. I'm not going to do it, honey. Don't worry.
I think my problem is that going to Mars, that's a really easy place to die on.
Oh yeah.
So if your goal is to die on Mars, it's really easy. And I've decided, no, I'm going to do that process here on Earth.
That's right.
Now, we've been talking about how science is weird and that science, sometimes you get into the egos and the positions and the prizes and all of these things that the trappings, I guess you could say. But sometimes somebody throws something out there crazy, which Einstein did with relativity, and it completely changed our outlook, our understanding of how the world of the big works, not quantum mechanically, but the world of the big.
Yeah.
And ever since then, it's been the best we had. Relativity is the best thing we've got because it seems to hold up. But there seem to be discrepancies, which bring in other people coming in, and many have. There are many. The road to defeating general relativity is littered with the corpses of theories.
That's right.
So we do have a few that are interesting, though, that might give relativity a run for its money, or at least parts of it. And one of those is MOND, Modified Newtonian Dynamics. As a cosmologist, what is your view of that theory? Do you think that has legs as far as pursuing to see if, well, maybe things go in that direction as opposed to our classical thinking on relativity?
Yeah, that's a very good question. So I had on the father of MOND, is Mordecai Milgram, as a professor in the Weizmann Institute in Israel, who had come up with this idea, really a solution for a while, kind of in search of a problem, and that was to modify the behavior of gravity at large scales, but kind of agree on shorter distance scales where we know that Newton's laws behave properly. And the way that he instantiated this was by adding sort of a scale-dependent constant or a parameter that changed the acceleration depending on the distance that one was talking about measuring. So at linear, this acceleration modification, if it varied by a very, very small amount as a linear function of distance, then at the small scales of Earth and even our solar system and even our local stellar neighborhood, you wouldn't ever notice any deviation. So you wouldn't see that, say, the orbit of Neptune or Maki-Maki or one of these Kuiper Belt objects, those would not show any observable deviations from standard F equals ma Newtonian dynamics. But for something in the MOND regime where things are behaving much differently and they're modifying the acceleration law, the F equals ma law, by maybe a quadratic dependence. So maybe the force depends not linearly on acceleration, but on the square of acceleration. Let's just make that up. There are some versions of that where that happens. So that's modifying Newton's second law. Now, the question is why? Why would you want to do something like that? And what would be the observational consequences of that? So the most successful that it has sort of shown itself to be is in the accounting for the so-called rotation curves of spiral galaxies. So we've known for quite some time that since the time of Vera Rubin, and she learned the techniques of doing the kind of spectroscopic Doppler shift velocity measurements of stars in various spiral galaxies from my late great colleagues here at UC San Diego in the 1960s, 70s, Jeffrey and Margaret Burbidge, who also came up, the two of them, with Willie Fowler and Fred Hoyle, the man who coined the term the Big Bang. They came up with the explanation for how all the heavier elements in the universe are formed in various star or stellar processes like supernova explosions and other phenomena. And they came up with that stellar nucleosynthesis. So they had tremendous contribution. Every now and then, John, I find a spectroscopic plate or a photographic plate in Margaret's office. I'm actually occupying Jeffrey Burbage's office right now at UCSD. And so, and it's kind of ironic because I study cosmology, and he was very much opposed to the notion of the Big Bang. He died an eternal skeptic and a proponent of the steady state. But we'll talk about that some other time. So these observations by Vera Rubin led to the discovery that the rotation of the spiral galaxy, of its stars in it, do not behave as the orbits of, say, the planets in our solar system do. In other words, it seems like there's more than just the central concentration of light does not correlate with the mass distribution of that galaxy as it does in the solar system. In other words, in our solar system, 99% of the mass of the solar system is contributed by the object that produces 100% of the luminous light in the solar system, and that's the sun. If you try to apply the same logic to the galaxy, thinking of a galaxy, a rotating spiral galaxy, as a kind of type of solar system, you find it doesn't behave that way. It doesn't behave where, say, Neptune is going much slower as 1 over the square root of the distance from, say, Mercury going the fastest. So it doesn't behave like that. And so it's been explained that one solution would be that there is an invisible cloud of dark matter, so-called halo, dark matter halo, many, many times larger than the visible light radius of these spiral galaxies. And in so doing, you can then extend the mass distribution without extending the luminous distribution of a galaxy's content. And that will then produce the kind of flattening or static rotation curves, stationary in the sense that the saturation of the velocity as a function of distance is what's observed. So you could do that using either unseen, undetected so far particles, sometimes called machos or sometimes called WIMPs, different types of versions of dark matter, but you wouldn't have to have any form of particulate dark matter at all if, instead of modifying the mass and matter content of our universe and invoking new forms of matter heretofore unobserved, but no, you merely kept the matter that we do observe, the ordinary baryonic, electrons, protons, croutons, my favorite particle, and you would then keep all those particles. You don't have to add anything new, but you have to change the F equals ma relation on the scale of galaxy rotation curves. So that's where Mordecai Milgram comes in and proposed this MOND, modified Newtonian Dynamics, in the 1980s, and that was then shown to be consistent with the rotation curves of galaxies. It is not all kind of sunshine, I guess, and roses, though. There are challenges to the theory of MOND that come from a variety of different approaches. So what MOND was doing, if you think about it, it's very common in science. What happens is we have a good working paradigm, a good hypothesis. We know that there are flaws in it, that there are gaps in our understanding, and then we propose a solution that corrects the inconsistencies of the pre-existing paradigm. And then that new theory can also be challenged by its own inconsistencies. There's no such thing as complete scientific 100% consensus on every aspect, and it's perfectly predictive, and there's no gaps, and the science is settled. That never happens. It's kind of a trope that such a thing is possible. So just as MOND fixes the problems of the dark matter paradigm, so too does MOND suffer from its own challenges. And we can get into those.
And one of those challenges with MOND is that it doesn't really completely eliminate the invocation of dark matter, right? Meaning that even with MOND, at least our ideas of it so far, without modifying the modified, that we're still going to need some quantity of dark matter to explain what we see within MOND, no matter what we do. So the problem of dark matter, the invisible matter that goes through walls and does all of the strange things that we think it does, it doesn't eliminate it, right?
Yeah, there are many different observations that challenge MOND in terms of its adequacy, its so-called causal adequacy. Is it sufficient to fully account for all observations? And I think it's fair to ask that question, but it's not the only question. That's not sufficient question. In that there's no, it is true that Newton's laws have these flaws in them at high energies, at high velocities, at incredible mass scales, but it also works and operates incredibly accurately on a wider variety of scales in sort of a logarithmic sense. So it passes more tests than it fails in sort of an abstract space of size scales and speed and energy scales. So to say that MOND can be sort of dismissed because it doesn't, I know you're not saying that, but to say that MOND has to account for every aspect of the physical world, I think is asking too much. And for example, we do know that dark matter exists. I actually have, I think it's one of my most popular kind of short video explainer videos, and it's called Dark Matter Was Detected. And it has to do with the only form of dark matter that we know for certain exists, and that's the neutrino. Neutrinos are weakly interacting massive particles. They are WIMPs, but they are not sufficient in their number distribution or their mass levels or the combination of those two parameters to account for the gap between the amount of matter in the universe and the amount of luminous matter in the universe. So they can't be all the dark matter, but they make up some of the dark matter. So to say that MOND has to make do without dark matter is over requiring a little bit too much.
Could it simply be that we are blind to dark matter? In other words, could it just be a matter of us not knowing how to look for it? In other words, look what we had to do to detect neutrinos. We had to build these big detectors with big, enormous amounts of water buried in the earth and things like that. Could it simply be that we're missing it? We're missing our ticket to detecting dark matter because we just don't know what to look for.
Yeah, that's 100% correct. And it could even be more terrifying than that. With what I study, which is the cosmic microwave background's polarization, in part to investigate whether or not the universe began with an inflationary epoch. It may be that inflation really did take place, and inflation really does produce gravitational waves, which then perturb the primordial cosmic microwave background signals, inducing upon them a special type of polarization called B-mode polarization. And that's all well and good. And that actually happens, and inflation occurred. But guess what? It may have occurred at such a low energy scale that it is theoretically impossible to ever make a detection, given the background sources of noise that would supersede by many, many orders of magnitude this primordial signal. Now, it could be, we hope that that's not the case for those of us that want to see inflation and understand the primordial perturbation spectrum in the universe. Well, guess what? The same thing could happen with dark matter, as you point out. It could be that dark matter is, honest to goodness, it's really there, and it truly exists, and there's all sorts of candidates, scalar fields, axions, WIMPs, all sorts of different hypotheses for it. And it could even be that MOND takes place as well at some level. But these effects are so minuscule that we can never possibly detect them because there are other backgrounds. Here at UC San Diego, my colleague Kai-Xuan Ni, working with past guest Alina April at Columbia University, they are leaders of the xenon one-ton experiment using liquid noble gas called xenon as a dark matter detector. And so they look for interactions between recoils and electronic events where they rely on a mechanical collision of these neutrinos, of these dark matter candidates, if they do exist, with ordinary matter via essentially unavoidable collisional effects. And that it would evade electromagnetic interactions altogether. And in so doing, they have to combat and confront what's called the cosmic neutrino background, that there happens to be a surplus of neutrinos produced in the same nuclear furnace that fused the lightest elements in the periodic table, namely the Big Bang nucleosynthetic process. And also, when supernova go off in our universe, about one every 100 years per galaxy, and there's an awful lot of galaxies in the universe, so they produce tremendous amounts of neutrinos too, as we learned from supernova 1987A. And so the universe is suffused with neutrinos, as I said, make for an unescapable background that you cannot remove those, because to remove those, you'd have to detect the cosmic neutrino background, and effectively you turn your dark matter experiment into a neutrino background experiment. And so you detect a lot of neutrinos, that's great, that's hard to do, but it wouldn't have the same impact as detecting dark matter. They would be buried beneath an avalanche of other noise sources. So that's kind of the nightmare scenario. Another nightmare scenario is that these particles of dark matter really exist, but they only interact gravitationally. There's no collisional way for them to interact. There's no scalar field. There's no modification of electromagnetic potentials that they induce. And that would make them effectively undetectable as well, even though they exist.
So let's assume for a moment that they exist. And you, as somebody that studies the CMB, and then we also have this idea of a neutrino background, do you think, and we're going to go to physics crazy town here, but do you think that there's any value in speculating that maybe there is a dark matter background, and that maybe the key to understanding the Big Bang, inflation, and things like that could be the study of dark matter early in the universe?
I'll see you're crazy, John, and I'll raise you some insanity. Let's go even deeper. Let's say there is dark matter, and just as matter, there's more than just matter. There's like protons and neutrons, but those protons and neutrons are the kind of non-fungible tokens of this subatomic world, and they, through their various interactions, can combine to make a beautiful, resplendent periodic table. Well, who's to say that you could have dark matter periodic table? In other words, not just one type of dark matter, but 116 types of dark matter, different permutations and combinations of some fundamental dark proton. Or, we know it can't be specifically that. We know it can't be a so-called supersymmetric particle. There are reasons to suspect that supersymmetry is not necessarily the complete description of the universe on its small scales. And so there's been a lot of hope that there be some analog of the neutrino, but in supersymmetry, where it would be a boson and it would not decay and therefore be stable. And there are physicists that spent their whole careers on that, and it seems unlikely given results from the LHC that such a scenario takes place. So yes, it could certainly be that there's a rich tapestry of dark matter, and there's nothing that precludes the complex tapestry from being even weirder than we can imagine right at this moment.
Do you think that the Big Bang, given that matter makes up normal matter, baryonic matter that we see, makes up such a small part of the universe, most of it has to be dark matter from what we see so far, that we're missing a puzzle piece in so far as Big Bang cosmology goes, where dark matter is the linchpin, and that this is a universe of dark matter that's created from a phenomenon of dark matter, and that we're missing the biggest puzzle piece of all by just not knowing what the nature of it is?
Yeah, and certainly that's not out of keeping with what we do observe in the universe, which is that the matter that we're made up of, not only luminous matter, protons and neutrons, but protons and neutrons and electrons that aren't constrained in extragalactic plasma. We're talking about like 0.05% or something, 0.5% at most of the energy budget of the entire universe. And yet we're incredibly important, right? I mean, we're the only form of matter that's conscious, that can contemplate where its own existence came from. So I think, again, to kind of ascribe importance to how much something represents on a cosmic pie chart or energy budget, I don't think captures the immensity of the problem that you're posing, which is that we know that most of what we see in the universe is the effect of unseen and potentially unseeable forces, dark matter potentially, or maybe some modification of Einstein or Newton, and dark energy, which we know actually less about. We have worse limits on dark energy as a candidate, or how it arises, than we do about dark matter. I mean, we have almost no constraints on how dark energy came to be, because to test it requires such fantastic sensitivity that it seems completely inconceivable from our current technological vantage point that we could ever glimpse it.
Do you think that hidden within these crazy town questions, do you think that the solution to the Fermi paradox may well be that aliens eventually just convert their existence to dark matter?
So now you put down the trump card of insanity. Now, I haven't considered that. Our mutual friend, Stefan Alexander, Brown University professor, has explored ideas related not only to things that would border on pertinent to your question, but he's also explored other ways in which dark matter could be invoked. In other words, not maybe thinking about it as particles at all, but more thinking about it as a fluid, perhaps even an exotic fluid called a superfluid, where you have correlations, spooky action at a distance, where you have dark matter Cooper pairs that interact across the cosmos. So he's more kind of in line with the type of line of argumentation that you're making than I am. I'm just a simple experimentalist. But so I couldn't speculate. The reason that we don't see aliens is because they're made of dark matter. It may be that that's true, but that also sounds potentially unfalsifiable. And it could be also something that you could say about any sort of undetected or unproven entity like a Sasquatch or something like that.
The Loch Ness Monster.
The darkness monster.
Yeah, the darkness monster. That's my favorite one. Is the Loch Ness Monster is made of dark matter. And it just changes state. So every so often you can see it, but then it goes away. But you could go crazy telling yourself stories about this kind of thing.
Given enough scotch, it would be a lot of fun, actually.
Actually, it would be, especially with scotch, because it's apt. Loch Ness and a decent scotch.
Nice
now,
scotch.
My last question for you is the most complicated one. Do you think that we're anything close to a complete understanding of the universe? Or do you think in 5,000 years, these questions are still going to exist and we have no understanding of the universe because the universe is not beholden to give us an understanding of it?
Yeah, so this is this ultimate kind of question of cosmic hubris versus cosmic humility. Do we say that we look upon the universe with all the tools and technology that my colleagues have invented over the millennia and marvel at the rapaciousness of our ambition to learn and explore more? Or do we say that the more we know, as I think Aristotle said, the more I realize how little I do know? And that's a kind of a consequence or a corollary of the famous kind of parable that John Archibald Wheeler, the man who coined the term black hole, came up with, which is he analogized science to sort of an island in the middle of an ocean. And the ocean was an ocean of ignorance. And the island size would grow the more knowledge that scientists could provide about the physical reality of the world. And so as the island grew, it is also increasing its coastline is increasing linearly with its dimension, and its area is increasing as the square of the diameter or the square of the circumference, proportional to that. So he analogized it that way. And in so doing, it kind of makes visceral this notion that you really do encounter more and more phenomena the more and more you learn. So I think it's an unwinnable battle. My late great father used to say, we're fighting a continual battle against an infinite army. And the army is the army of all the things arrayed against us by nature. But that army is always in retreat. It's in a perpetual state of retreat, unlike the valiant, say, Ukrainians and Zelensky's. They're in retreat. And so we can take some comfort, but maybe that's false comfort, that we're really learning very little and grand sweep of things will never really come close to knowing any bit more than, say, my dog when he looks up at me and tries to understand, what am I doing with this yellow shaped stick and why am I pulling it across a piece of paper to talk to my kid? He doesn't understand it. He just wants me to throw him the stick. So I don't know. I don't know if we can ever approach it, but you know what? It sure as hell is fun trying to see how much we can learn about the reality of the universe.
All right, Brian, thanks for joining us again. We'll do it again sometime, and I look forward to sipping a nice scotch with you alongside the dark matter Loch Ness Monster. Now, tell everybody what's going on with the channel, and are you writing a new book?
So the books are kind of on hiatus now. I've written 3, and I produced the first ever audiobook by Galileo last year, 2022. And so I've slowed that down, kind of that output. I'm focusing mainly on getting the Simons Observatory, the world's highest and most ambitious cosmology experiment, over $100 million project that I get to co-lead with my colleagues at the University of Pennsylvania, at Princeton, at Berkeley, in Chicago, and here at UC San Diego. And we have 300 of the most brilliant scientists in the world working to understand not only the origin of the universe, as if that weren't sufficient, but also how it's evolving, composed of, the structure of galaxies, and even maybe look for one of your favorite topics, Planet 9. And maybe we'll see some signals of distant alien civilization. So on the work front, that's keeping me pretty busy. And on the creative front, I am really enjoying the podcast and having great interviews with great authors. As I said, I had on Mordecai Milgram, and I'm having on Stacey McGaw, who's the kind of got the torch passed from Mordecai Milgram on the MOND front. I'll be talking with some more Nobel Prize winners. I've talked to 14 Nobel Prize winners so far on the podcast, and many more to come. And really enjoying just kind of giving back to the public. Our audiences are the smartest in the known universe, and I just love to share the hottest cutting edge discoveries that my colleagues are making in a way that an ordinary person can understand, appreciate, and hopefully be inspired by. So that's what I'm up to.
Indeed, greatest audience in the world, especially. I marvel at some of the things that people post to me, just the most amazing ideas that I'd never thought of. And it's very rewarding being a YouTuber reading your comment section, as I'm sure you know.
Yeah.
All right, Brian, thanks for joining us, and we'll do it again.
Thanks so much, guys.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.